Hello friends, welcome to lecture 8.3 in the unit on discrete wavelet transforms. In this lecture, we will continue with our discussion on multi-resolution approximation and primarily talk about wavelet filters and also look at how the DWT is implemented using the celebrated pyramidal or fast algorithm due to Mallet. So, the specific objectives of this lecture is to discuss scaling function filters. If you recall from lecture 8.1 we talked about DWT as CWT evaluated on at specific scales and translations, and then in lecture 8.2, that is the previous lecture, we exclusively talked about approximations, the scaling functions that are responsible for generating those approximations, and in particular the multi-resolution approximations generated by the scaling functions. In the concluding slide of the previous lecture, we introduced what is known as a low pass filter that is associated with the scaling function. Today we will talk more about that, and then we need to complete the picture by talking about the details. When we say details here, we are not referring to the details of the lecture, but the details of the function that are left behind during the approximations. And these details are generated by wavelet basis. In particular, we are interested in orthonormal wavelet basis, and of course associated with these are the high pass filters. So, these are complementary to that of the scaling functions and the low pass filters. We shall look at those, and as I mentioned earlier, we will look at the fast algorithm for computing DWT, the pyramidal algorithm, and finally talk about perfect reconstruction, that is how to synthesize the signal back from its approximations and details. In this process, we shall look at a couple of examples. This lecture again is largely theoretical with some examples, illustrated examples. In the next lecture, I am going to show you how to compute or how to perform the discrete wavelet transform in MATLAB. So, let us quickly recap the concept of multi-resolution approximation. Essentially, multi-resolution approximation is a collection or a set of embedded approximations. So, these are not collection of any arbitrary approximations, but so called embedded approximations embedded in resolution spaces that are differing by a factor of 2, and we also call them as nested subspaces. So, if you look at any scale m or any level m, then the Vm is the subspace of the corresponding to the approximation at that scale. So, all functions in Vm are approximations of a signal x of t at that level m. That is how you understand a subspace. This Vm is embedded in Vm minus 1, because m minus 1 corresponds to a finer resolution or a finer scale, and in turn this Vm contains a coarser approximation Vm plus 1 and so on, and you extend this nested subspaces from minus corresponding to m running from minus infinity to infinity. So, if I were to simply illustrate graphically, this is how it would look like. So, I have here a subspace. Let us say this is my subspace V naught. Within this subspace is V1. So, this entire thing is V1, and then you have V2 and so on, and in fact V naught itself is contained in V minus 1 and so on, that is the subscripts are the values of m. As I mentioned yesterday, normally we assume that the signal that is given to us in the sample form is living in this subspace V naught, and we can only construct coarser and coarser approximations. To get a finer approximation than the sample signal that I have, I need to sample faster, so that I get a signal that is an approximation of x of t, the continuous time signal that lives in minus 1 and so on, V minus 1. Now, today what we are going to talk about is the gap that is left out when you move from V naught to V1. This space we call as V1. And once again when I move from V1 to V2, the details that are left out are contained in the space W2 and so on. So, as you can see, these spaces are inclusive. Which spaces? V0, V1, V2, V minus 1, they are inclusive, and as m goes to infinity minus infinity, it would consume the entire real space. In contrast here, that is as far as inclusion is concerned, W1s, W2s, and in fact if I draw another subspace V3, then associated with this approximation space is a detailed space W3, they are all mutually exclusive. So, W1 is not contained in W2 and W2 is not contained in W3, you can design it your wavelets in such a way. These V's are generated by the scaling function. So, V0 is generated by the scaling functions and they translates at level 0. V1 is generated or is spanned by the basis functions phi1 of t and there translates and so on. So, the specialty of each of the scaling functions is that they are orthonormal. Right. So, that is the main feature of a multi-resolution approximation. So, that is the second point that we are making, the scaling function and its integer translates constitute an orthonormal basis for Vm. And when you want to obtain an approximation of x of t at any level m, then you implement the orthogonal projection. In the previous lecture, we had looked at the definition of orthogonal projection and we also learnt that orthogonal projection yields the best approximation of the signal on to a subspace V. Here the subspace is Vm. So, how do you compute this? Well, using the same expression that we had learnt earlier, x hat, that is the convention that we follow to denote an approximation. The subscript m denotes the level at which you are approximating. That is the orthogonal projection of x onto the subspace Vm. Essentially what you are trying to do is you are re-expressing your signal x in terms of the basis functions that span Vm, and the coefficients of this expansion of x onto the basis functions that span Vm are denoted as a subscript m n. So, n keeps track of the index, the translation index, and m is keeping track of the scale at which you are approximating or level at which you are approximating. And because the phis are orthonormal, we know that these coefficients themselves, the a m subscript n, which are known as the approximation coefficients, x hat is known as approximation, a subscript m n is known as the approximation coefficients. They are computed simply as the inner product between x and the basis function themselves. That is again you should go back and refer to the previous lecture for this expression. So, this is the expression that we use for computing the approximation, and the approximation coefficients themselves are computed as inner product between x and the basis functions. We will see a similar expression for the detail component that is left out as a result of this approximation, where we will have what are known as detail coefficients and the scaling functions would be replaced by their corresponding wavelet counterparts. One of the fundamental equations that comes out of MRA, which is what we had seen in the previous lecture, is a so called scaling equation or the scaling relation, and this stems from the property of the MRA, which says that the subspace at level m is contained in the subspace at level m minus 1. It's pretty much like saying V1 is contained in V0 and V2 is contained in V1 and so on. So, you look at two successive subspaces and write the relation between the basis functions that span these subspaces. So, the basis, so if I choose m equals 1, then we can say V1 is contained in V0 and the basis functions that span V1 are the phi subscript 1 as I had written on the board, phi 1 of t and its translates, and phi 1 of t by definition, if you recall, phi 1 of t by definition is 1 over root 2 phi of t by 2, right, and then of course it translates, but we can pick one basis function in V1 and then rewrite what it means by saying V1 is contained in V0 is, as I had explained earlier, any function in V1 can be expressed as a linear combination of the basis functions in V naught. So, any function in V1 is also the basis function. So, I pick 1 over root 2 phi of t by 2 as one of the basis functions and express that as a linear combination of the basis functions in V naught. The basis functions for V naught are phi of t or phi naught of t, we do not use the naught, phi of t and its translates, and the coefficients of this linear combination are your h of n. Notice that h is a discrete sequence, whereas phi of t is a continuous valued function. So, there is a big difference between these two. And how are this h computed? Well, because phi is orthonormal, we know that, we can straight away write h as the inner product between the 1 over root 2 phi of t by 2 and phi of t minus n. That is the beauty here, because we have an orthonormal basis. The expression for h of n is very simple. Now, what is the greatness about this equation? Well, this is a fundamental equation governing DWT, because as you will see later on, it allows me to compute approximations, in fact approximation coefficients a m of n from a m minus 1 or a m plus 1 n from a m of n and so on. Because the basis functions themselves satisfy this scaling relation, the coefficients which are computed as the inner products between the signal and these basis functions will also share a similar relation. That is the main idea, and this gives rise to the fast algorithm that exists for computing DWT. Now, this h of n, which is a discrete sequence, can be given the interpretation of a filter, primarily because if you look at equation 3, it is a convolution equation. So, h of n, it is a convolution of phi of t with h of n. So, you are pumping in phi of t, you are injecting phi of t into a system whose impulse response is h of n, and that produces 1 over root 2 phi of t by 2. So, that is how you view this as. Therefore, from linear systems theory, we know h of n can be given a filter, the impulse response of a filter interpretation. What kind of a filter are we looking at? Well, low pass filter, because we know that as I move from one subspace to another subspace, I am approximating further, and every approximation is a low pass filtering operation, and therefore, h of n acts as a low pass filter. In fact, the other way of checking whether it is a low pass filter or not is to see if h of omega, which is a Fourier frequency response function of this filter, if that is non-zero at 0 frequency. If that is true, then h acts as a low pass filter. It turns out that the moment you say phi of t is a low pass filter, which means phi of omega itself at omega equals 0 should be non-zero. If you translate that condition to a condition on h, then you can show that h is a low pass filter. We will not show all of that, but we will just talk about those results. Now, the key point here that makes it complete distinct from CWT is, in CWT we have primarily used directly the wavelets, or in fact we hardly worked with scaling functions, we only worked with wavelet functions, and we directly use the wavelet functions. We never talked about the associated filters, but now in DWT, instead of using the phi of t to construct an approximation or the psi of t to construct the detail, we shall use the corresponding filters instead. That is, now we have h of n as the low pass filter associated with a scaling function. We need to only work with h of n, we do not have to really work with phi of t. Why? Because all requirements on the scaling functions can be translated to constraints on the impulse response or the low pass filter impulse response coefficients, and that is the beauty here. By the way, before even we talk about how the constraints on phi translate to constraints on h, you may also note that equation 3 could be written for any subspace, two successive subspaces in general. For example, I could write the expression, I could write the basis function for V naught in terms of basis functions for V minus 1. So, that is the equation that you see here, phi of t is root 2 sigma h of n phi of 2 t minus n. Notice that the h remains the same, whether you are looking at basis functions for V naught in terms of V minus 1, or basis functions for V1 in terms of V0 or in general Vm in terms of Vm minus 1, the coefficients or the filter that relates to successive approximations is the same, and this is what you should remember, right. But this is only true for 2 successive approximations. Now, let us see how the scaling function constraints translate to those on the impulse response coefficients H. Now, we avoid all the proofs. This is the probably the longest and the central result. I mean, the proof associated with this result is one of the longest ones if you look at Mallet's book, and this is a central result because it helps you move from the scaling function space to filter space, and thereby implementing all your approximations using some filtering algorithms, special filtering algorithms. So, you can show that the 2 primary constraints that we have on the scaling function, one that they should be orthonormal, and 2 that it should be a low pass filter, right. So, orthonormal would mean integral phi of t minus n is 0 for all n not equal to 0. So, orthonormality on phi of t, that is at any scale, let us pick V0, orthonormality would mean this integral from minus infinity to infinity is 0 when n is not equal to 0 and 1 when n equals 1. So, there should be a dt. This 1 essentially means that we have normalized the scaling function to have, in fact we can say phi square because phi is real, it is normalized to have unit energy. So, this is one of the prime requirements on the scaling function even for us to be able to generate the MRA. And then the other requirement is that phi of omega should be some constant alpha greater than 0, but less than infinity. This requirement stems from, this condition stems from the requirement that phi is a low pass filter, right. So, these are the 2 prime conditions. Now, these 2 conditions translate to the conditions that we have on the slide on the impulse response coefficients. As I said, we avoid the proof. The condition of orthonormality can be written directly in terms of the impulse response coefficients or in terms of the FRF of the filter, FRF meaning frequency response function. So, the h of omega, which is the discrete time Fourier transform of the impulse response as usual, as with the standard definition of a frequency response function, that is what we have. So, any sequence that satisfies these conditions, and then there is another mild condition that is sufficient, not really necessary, constitutes or qualifies to be a low pass filter that can be associated with a scaling function. So, I can start off with this low pass filter and I can generate my scaling function. Now, you understand how the Dobeschi wavelets are arrived at. Remember, when we talked about scale to frequency conversion in CWT, we talked about Dobeschi filters and we said there are no closed form expressions for Dobeschi filters. Instead, they are generated by specifying the low pass and high pass filter. So, this is a connection now. The Dobeschi filters are arrived at by additionally imposing some requirements on H, but the basic idea is to design H first, and then from this H you design your phi of t or you compute your phi of t iteratively. That we will talk about in one of the subsequent lectures, how to arrive at phi of t, how to compute the scaling function starting with a low pass filter. What we are looking at it now is how constraints on phi of t translate to constraints on H. Now, the constraint here that you see in terms of h of omega for orthonormality of scaling functions can be arrived at by writing the scaling relation that we saw earlier in the Fourier domain. So, this is the scaling relation that we had in the time domain. If I take the Fourier transform on both sides, then I can arrive at the equation 7 which is relating the Fourier transforms of the scaling functions. Okay. Because you are taking Fourier transform of phi of t by 2, the Fourier transform becomes phi of 2 omega, whereas the Fourier transform of phi of t would be phi of omega, and t minus n would be phi of omega multiplied by a modulating factor or an exponential, and then requiring that phi of omega equals 1 at omega equals 0. In fact, they should read phi of 0 equals 1, not phi of omega equals 1. At 0 frequency, the scaling function should have a Fourier transform value of 1, so that the scaling function acts as a low pass filter. That is it. So, instead of working with phi of t, now we will work with the impulse response coefficients that satisfy the conditions given in 5 and 6, and this discrete filter is known as a conjugate mirror filter. We will learn the reason for this name when we talk of reconstruction shortly. As I said, one of the prime things that we shall do in this lecture is to complete the picture, that is, we have talked about approximations until now. Now we are going to look at detailed spaces, and as I explained to you earlier in the sketch, we had V's and W's. Now we will ask what basis functions allow me get those details. Well, I already know the answer, they are the wavelets, but can I come up with some special properties of the wavelets? What are the, how are these wavelets related to the scaling functions? I do not want them to be loosely I want them to be tied together, that is the main thing. Now that tie comes through the fact that the details at level m are contained in the approximation at level m minus 1. So this is to say, why is this true? Because when I move from approximation at level m minus 1 to a coarser level m, then I always leave behind some detail. That detail is associated with the approximation at level m. So we call that as a detail at level m, and therefore we say that the detail at level m are contained in the approximation at level m minus 1, because m minus 1 is a finer approximation. How are these details computed? Well, they are computed by projecting x of t onto the bases that span this detailed space, and the bases that span this detailed space are the wavelets, because they are essentially band pass filters and so on, and by so the wavelets at that scale and their translates, and that is what this means here, psi of m comma n, n belonging to z. So psi of m is the basis function at scale m, and its translates together constitute the family of basis functions for what we call as a Wm, which is a detailed space. We have introduced this notation earlier as well. So denoting now the detailed space at level m by Wm, I can write Vm minus 1 as the orthogonal sum. This symbol here means orthogonal sum. I am actually or you can say Wm is the orthogonal complement of Vm. At the moment we are not imposing orthogonality, but what we are saying is sorry what we are saying is that we sum up these two spaces not in the regular addition sense, but in a linear algebra sense, then we obtain Vm minus 1. Intuitively what this means is, when I take the approximation and detail at level m and put them together in a particular manner, not by direct addition, then I get the approximation at a finer level Vm minus 1. In terms of the projections, the approximation at m minus 1, we saw this relation yesterday as well, x hat of m minus 1 is x hat at m. So x hat at m minus 1 is a projection of x onto Vm minus 1, is x hat of m, which is a projection of x onto Vm, plus the detail at scale m or level m, which is a projection of x onto Wm. This is the same equation that we have seen in the previous lecture as well. Until now we have not talked about any orthonormality of this wavelet basis. Once again, to compute projections, it is ideal to have these bases as orthonormal, and the fact is that it is possible to construct an orthonormal wavelet basis as well from the orthonormal scaling function. So which is nice. I have already orthonormal scaling functions. By the way, when we talked about MRA, one of the things that we did not mention is the result which says there exists an orthonormal basis that you for computing the MRA or constructing the MRA. That is very important. We have avoided those theoretical proofs, but it is proved already that given an MRA you can always find some orthonormal scaling function that will allow you to generate the MRA. So, we have the orthonormal scaling function. Now, we want the orthonormal wavelet basis, and the fact is we can find such an orthonormal wavelet basis. Very important, until in the equations 8 or 9 there is no need that the basis wavelet bases are orthonormal, but now we want the orthonormality. And how do we achieve that? This is the subject of the next couple of slides. The first thing that we note, the first point that we note is Wm is a subspace of Vm minus 1. Wm is contained in Vm minus 1, that is the details are contained in the details at level m are contained in approximation at level m minus 1. Once again, as we argued earlier, what this means is the basis functions for Wm can be expressed as a linear combination of the basis functions in Vm minus 1. So, the basis functions for Wm, let us say m equals 1. So, W1 is a subspace of V naught. The basis functions for W1 are psi of t by 2 and its translates, and the basis functions for V naught as usual are phi of t and its translates. So, I pick one of the basis functions for W1 which is psi of t by 2, in fact 1 over root 2 psi of t by 2, and express that as a linear combination of the basis functions of for V naught which is phi of t and phi of t minus n, its translates. These coefficients now are complementary to that of h, that is the beauty here. Earlier I had h and now I have g. The notation is also chosen so that you can see the complementary characteristics of g and h. Naturally, you should expect now g to act as a high pass filter for two reasons. One, because I know wavelets are high pass filters, and two, because the details are complementing approximations, and approximations are characterized by low pass filters, therefore, details should be characterized by high pass filters. And in terms of the imposition on psi, for psi to be a low pass filter, we have already discussed that many times in CWT. The value of the Fourier transform of the wavelet at omega equals 0 should be 0. Now, this g can be computed once again as an inner product between the wavelet at scale 2 or level 1 and the scaling functions at level 0. Because phis are orthonormal, I have a nice expression for g. Once again, this has got to do with the projection property associated with the orthonormal basis. So, g is a high pass filter. Now, what remains to be done is to make sure that my wavelets are orthonormal. How, what kind of constraints now exist on g? Sorry. As we said, as we observed earlier, constraints on the scaling function can be translated to constraints on the low pass filter. Now, requirements on the wavelet can be now translated to constraints on the high pass filter. So, h for phi, g for psi. Whatever I want for phi, I can dictate certain conditions on h. Whatever I want for psi, I can dictate certain conditions on g. What do I want now? I want psi to be orthonormal and I want psi to be a high pass filter, right. So, we will just look at the orthonormality requirement. The high pass filter requirement is naturally satisfied the moment you formulate express the scaling function as a linear combination of the the wavelet function as a linear combination of scaling functions. We are more worried about orthonormality. You can once again show that the orthonormality requirement for the wavelet at any scale m, if I take psi of m subscript m comma n, if I want it to be orthonormal, if this basis should be orthonormal, then the associated high pass filter should satisfy these conditions given in 12 and 13. Once again, I avoid the proofs, I am directly giving you the conditions. Now, these conditions are in terms of the frequency response function of the high pass filter. It turns out that you can show both these conditions 12 and 13 are satisfied the moment the high pass filter shares this beautiful relation with the low pass filter. Okay, it is like a reflection with the sign reversed. So, all your and that is well known in filtering literature, the standard filtering theory literature. If I want to construct a high pass filter, I take a low pass filter and I can reflect it and so on. But this is a special reflection, and this G and H are now tied together. This tying together is coming due to the fact that I have required Wm to be one, that is two conditions, Wm to be a subspace of Vm minus 1 and Wm to be orthogonal to Vm. So, these two conditions have produced this 14 on the filter coefficients. So, now you should see the big picture. We start off with CWT where we only talk about wavelets, then we move to DWT where we saw that the approximations that I construct have some special features, MRAs. So, now I am interested in the scaling functions, and then we said instead of scaling functions I can talk about the associated low pass filters, and then we said we want to complete the picture by talking about the details as well, which are produced by the wavelets. So, the scaling functions and wavelets are complementary. The low pass filters and the associated high pass filters are also complementary. When I want orthonormal wavelet basis, then these filters obviously intuitively have to be tied together, and that is given in equation 14. That is it. So, I start with H. All I have to do is I have to design H, then G is fixed. Once H and G are fixed, I just compute my approximations. I compute my phi of t and psi of t, and then compute my approximations and details. So, this is let me just illustrate that workflow for you in a schematic. So, I have H, I start with the design of this low pass filter, and if I want orthonormal decomposition, that is approximation and detail should be orthogonal, then that condition automatically fixes the associated high pass filter. So, from H of n I design G of n, the high pass filter, and this low pass filter generates a scaling function. From this high pass filter also I can generate the wavelet, not only at scale 0, but at all scales. Of course, once I know phi of t and once I know psi of t, the wavelets, the scaling functions and wavelets at other scales are automatically known because of the relation, right. I know phi m n of t is nothing but 2 to the minus m by 2 phi of 2 to the minus m t minus n. I know this, and likewise for the wavelets. So, once I have this and once I have these as well, the scaling functionlets and the wavelets, then I can construct a m of n, the approximation coefficients at any scale, and the associated coefficients, detailed coefficients at any scale. Now, what we shall learn is a very important fact, that we can compute these approximations and details completely bypassing this step. We do not have to really compute the scaling functions and wavelets at all, although the expressions for a m and d m are given in terms of projections of x onto the respective basis, that is phi of phi and c, or phi m comma n and c m comma n. We can avoid this step completely, and that is what is the beauty of the fast algorithm that exists for DWT.